Welcome to this follow-up lecture on pound calculus. We introduced pound calculus yesterday, and perhaps the most intriguing thing in pound calculus is really the notation. So I recall some of it. The framework is we assume we have a process that is stationary. We observe something of the process which is invariant by change of time origin and depends on the process state, possibly the history and the future. Also associated with this is a sequence of events of time instance, which is called a stationary point process, that also has the same property of being jointly stationary with ST, and which typically is derived from specific transitions in ST. So in this framework, we call expectation with a little zero, that's the pound expectation of something, for example, XT, is the expectation or the average of this when we sample it at an arbitrary event time, which corresponds to what we do in simulations. When we calculate the pound expectation of something, we estimate it by taking the average of the quantity of interest observed at time instants that are of this specific point process. In contrast, we also define the stationary probability of something as the time average. That's the integral or the sum in discrete time of what we can observe divided by the total observation period. So that's those two different things that correspond to, in statistics, what we can call different sampling methods or different viewpoints. Yesterday, we saw one of the two pound calculus formula we will see, the first one called the intensity formula. That's a very simple formula, but very useful. That says that the average number of events that you will see in this framework is equal to 1 over the pound expectation of the time between two consecutive events, which is captured by this formula here. And as we saw yesterday, this requires only stationarity. Of course, it's true for Poisson process or for events such that the time interval between events is IID, but this goes well beyond. Today we start with the second pound calculus formula, which is called the inversion formula, which takes this form. So let's try to understand what it means. So here I'm observing some quantity x at some time t, and recall that x of t is supposed to be jointly stationary with the simulation state here. So that means we are looking for the viewpoint of the time average. An inspector that comes at an arbitrary point in time will sample the system, will do some calculation, apply some calculation to obtain some metric, and what she estimates is expectation of x of t, which therefore is also equal to the expectation of x of 0 because time is invariant. Here we have a stationary process. So that's the viewpoint of coming at an arbitrary instance. Instead, we can relate it to an expectation of something that is computed at specific instance of the point process Tn, but it's not the expectation of x, it's the expectation of the integral of x between 2 points of the point process. And because now we are changing it, we need to rescale, where the rescaling quantity is precisely lambda, which is the intensity of the point process, the number of events per time unit. So in English, that means that the expectation of xt taken at an arbitrary point in time is equal to the expectation of an integral that is the integral of the thing of interest between two specific arrivals of events. So this, of course, is this integral is itself a random quantity because the times at which such events occur are random. But if we take here the pound expectation, that means we condition upon the fact that at time 0, there is precisely an arrival, which is the pound calculus way of saying we estimate this integral between two arbitrary transitions of the point process. If we take two arbitrary transitions, their durations are random, x is random, so everything is random, but the integral itself is obtained through a deterministic calculation. Then we take the average of that, when overall randomnesses that are possible, multiply by lambda, and that gives exactly the same. If you think about it, it's not such a surprising formula, because you say, if I am between t0 and t1, the average that I will say is this integral divided by t1 minus t0. And over the long run, the expectation of t1 minus t0 is 1 over lambda. So I have the lambda term here that replaces this rescaling. Intuitively speaking, this is where it comes from. But the nice thing is that's a strictly correct formula. It's true for any framework that we have, as I discussed, where we have a stationary state and stationary point process and a quantity x of s that can be observed from the simulation itself. Let's apply this to a very simple example, but that's also a very classical example in stochastic modeling, which leads to what is called Ferris Paradox. That's the waiting time, calculation of waiting time. So I assume here, my process is how buses run in a city, and I observe things at one bus stop here. So at my point process is the arrival of buses here, shown by a bar on this horizontal axis. And I call x of t the waiting time for an observer who arrives at time t. So that's the waiting time that you and I will experience if we come to the bus stop and have to wait for the next bus. Here I have to assume that the system is stationary. So the system is stationary. That means that those arrivals are not synchronized with time. So they are randomized. For example, even if they are periodic, we don't know the clock. We don't know at which period those things are occurring. So, which is a way of making the system stationary. Of course, if those arrivals are periodic and I know exactly at which time a bus arrives, then xt will not be random. But that's not what we assume here. We assume it's random because I don't know exactly the times at which the buses will arrive. And again, I make that stationary by randomizing the phase of my clock with the phase of the buses. So that's the variable xt here. I'm interested on the viewpoint of me and you, or a random observer coming into the system at an arbitrary point in time. We will experience an average waiting time until the next bus, which is expectation of xt. The Palm inversion formula tells us that this is lambda, lambda being the intensity, how many buses per hour are visible, times the Palm expectation of this integral. So let's understand what that takes. Well, first, let's compute the integral. The integral is the integral from t0 to t1. Remember that under the Palm expectation, t0 is assumed to be an arrival of a bus. So to compute this, we place ourselves in a situation where we know for sure that 0 was a bus arrival. And then we have to compute the integral from t0 to the next bus arrival time of the quantity, which is x also, but now sampled at a time s, which is an arbitrary point in time between t0 and t1. Now, if s is between two bus arrivals, then the waiting time is t1 minus s, because the next bus arrival will be at t1. So this integral is simply the integral from 0 to t1 of t1 minus s ds. So remember, things may look intimidating here. T1 and T0 are random quantities, but as long as we're concerned with computing the integral, we don't care. The only thing that matters is the integration variable s. So that's a high school integration exercise. What is the integral of a function t1 minus s with respect to the integration variable s? The answer is a primitive is 1/2 t1 minus s squared with a minus sign in front. So if I evaluate the integral, I will have the value at 0 minus the value at t1, which gives exactly this, 1/2 of t1 minus t0 squared. So this integral is this. Of course, it's random. So now the theory says I need to take the Palm expectation of this random thing. So it's multiplied by lambda, that gives lambda over 2, Palm expectation of t1 minus t0 squared. Now, apart from papers that talk of Palm calculus, usually we don't speak of Palm expectation. So it's important to know what is exactly the interpretation of this. This is the expectation of the time between two arbitrary consecutive bus arrivals. So it's the average of the square of the interval between buses in a simulation where we are a long simulation where in total we have capital N such events. We would estimate it probably like sum of Tn plus 1 minus Tn squared divided by N. So that is exactly what this formulation is giving. We can massage it a little bit more. So we have found this quantity here. Now, if I know the time series of all the consecutive bus arrival times at this bus stop, I can also compute the variance of the inter-arrival time. I call it V. So it's a palm variance, if you want. It's the expectation of the square minus the square of the expectation. That's the standard formula for variance here. And again, in real life, what people would say is I have a sequence of variables, Tn's, and of inter-arrival, Tn minus 1, and the V that we're speaking of is the variance of Tn plus 1 minus Tn. So that's the variance of the time that between two arrivals at the bus stop here. And if we massage this formula, the expectation of the square is the variance plus the mean to the square. The mean is 1 over lambda. So it gives us finally this formula. Expectation of the time until next bus arrives is 1 over half lambda plus lambda over 2v. Now let's understand this first term. 1 over lambda, we know from the intensity formula, is the average time, the average interval. So that's the average interval divided by 2. So that's 0.5, the mean time between buses. That's what we could call the system's viewpoint. If I am giving statistics as a system operator, I could say, in average, there is a bus every 20 minutes. Therefore, your average waiting time will be 20 divided by 2 equal 10 minutes. This is what institutions and developers would tend to give as estimation of their waiting time. But the true formula, the waiting time as experienced by a customer, will be this plus lambda over 2v. Now, v is a variance, so it's always positive. In extreme case, it can be 0, which means that the expected waiting time is always larger than 1/2 of the time between buses. If there is a bus in average every 20 minutes, then your waiting time in average is likely to be more than 10 minutes. This is a paradox because in average we say, yeah, there's a bus every 20 minutes. So in average you come in the middle, but no, in reality, the experience you will do will lead to an average that is larger than 20 divided by 2. Intuitively, why is that? Well, we can see on this figure, there are small interval and large intervals. When the interval is small, your waiting time is small, but you're also less likely to come in such a small interval. So when you come at random into the system, you sample more often the large intervals than the small ones. And this is captured by this penalty term here. You may remember in queuing theory a formula that had this similar flavor. It was called the Polacek-Khinchin formula, when we had the single server queue with Poisson arrivals and otherwise generic service times, the so-called MGI1 queue. For such a queue, we saw that the average number of customers and the average waiting time was negatively impacted by the variance of the service time. So the explanation of that comes exactly from also a palm inversion formula. And here we have, in the simplest of all cases, we have where it comes from. In the limiting case where V is 0, that means the buses are perfect. There is never any delay nor any advance. They come completely synchronously according to schedule. Then this penalty term goes to 0. But this is extremely unlikely in practice to occur. Let's return to our example, motivating example that we saw yesterday to explain the differences in two viewpoints as they can be given by system developers versus users of an information systems. That was the gatekeeper system where we said a job arrives at an arbitrary point in time. We don't know exactly when jobs arrive. When a job arrives, it will be served by the next opportunity where the task wakes up. And in this system, the task wakes up. There are two tasks that can process the job. And depending on which task you will have an execution time, which is short or long, depending on which task you take. But here, the wake up time of the tasks was alternating with very different inter-wake up times here. This is what we saw yesterday. And we saw because of that, there was a difference between the average execution time when a job arrives, if we ignore the waiting time until the next wake up of the task, which in this case is very small compared to the execution time here. When a job arrives, it's served either by a red or a green, and the system viewpoint would be to say, well, I take the average of the two, but we saw also that this is not correct, and we had, with the heuristic method of yesterday, a formula to that. Let's see how the same thing can be obtained exactly with the palm inversion formula. So I call x of t the execution time of a job that would arrive at time t. So it is given by the value of the arrow that follows t here. So the time stationary viewpoint, which is the viewpoint of the customer, is given by this application of the inversion formula, lambda times, again, the expectation of this here. So what is the expectation of this? Well, here, I should specify what is the point process Tn. So Tn is the wake up time of the gatekeepers. So those are the times at which there is an arrow here. Right. So what is this here? Well, the execution time when you arrive inside an interval, it's the time of is the value of the arrow at the end of the interval. So if I'm in the interval T0, T1, here is the value of execution between T0. I guess it should be 1. It's x1 is the value of the next job times T1 minus T0 here. So that's the value of the execution time at the end of the interval times the interval here. And now I have to take the palm expectation of this. So let me correct this typo here. X1. Oops, this is correct. Now, what do we need to do? We need to evaluate. So the calculation of this integral here was trivial. Here we need to calculate this palm expectation. And this palm expectation simply means, again, we look at the sequence of events. The events define intervals and values of arrows. And here what we mean is the expectation of the cross product of the interval and the value of the arrow at the end here. So by the same calculation as we did the last time, the expectation of a cross product can be expressed as the covariance of those two quantities, where the quantities are x1 and not x0. Is equal to the covariance plus the expectation, the product of the expectation. That's in fact the definition of a covariance here. So I'm given here. Whether it's for a standard expectation or a conditional expectation is the same. A conditional expectation is a special form of expectation here. So if we put all this together, we find at the end that our expected job execution time for a job that arrives at an average point in time will be equal to lambda times the covariance of the two quantities I mentioned, plus a quantity which is exactly the average of the two here, the expectation of x1. So if I take an arbitrary arrow, what is the value that I have? Well, with probability 1/2, an arrow gives 5,000. With probability 1/2, it gives 1,000. So that's the 1/2, the sum of the two, which is exactly the system viewpoint. So we find here exactly the same formula as we had found yesterday. The goal of doing this was simply to show that, in fact, the inversion formula is simply casting in a more formal way exactly what we do with the large time heuristic. Except here we don't need to do intermediate calculations at the expense of understanding what these little zeros in the pound expectations mean. If we return to our bus stop example, we find this result here, which is quite famous in queuing theory, which has to do with so-called residual time. We can interpret the time until the next bus stop arrives as the residual time, is the time until something that has started, for example, at the previous event will complete, because the next event will come to kick it out. So more abstractly, I have, as before, a point process with instant Tn, and I'm interested in three quantities. Xt, that's the one we've given before. That's the time until the next point. That's the time you wait until the next bus comes, and that's probably the time of interest if the example is really a bus at the bus stop. We can also ask, what is the time since the last event? In other contexts, that may be interesting. So how old is the thing that has arrived here? So y of t is the time you would have if you reverse time, or it's simply the time that has elapsed since the last bus stop. You could also ask the question, what is the time of the interval that I'm in now? So I arrive at the bus stop. If I had an inspector of the bus company there, perhaps the inspector could have recorded all the bus arrival times. And when I arrive now, I will wait until the next bus arrives. And based on that, I will sample a given bus inter-arrival time. So I call this ZT here. And the thing we would like to know is, how does the distribution of each of these random quantities compare to the distribution of the inter-arrival time? When we perform a simulation, like for the random waypoint, what we inject, for example, into the simulation would be this distribution of the time between events. How do they relate is given by this formula here and there. So if I call f sub t with a little zero, I do this here just because I am in the pound calculus chapter to recall that this is a pound distribution. This is the distribution of the time between arrivals. And it's a pound distribution because it's the distribution of something that is sampled at event instance. In contrast, I am interested in fx and fy, which is the PDF of the random quantity xt, waiting time, and yt, time elapsed. Then the answer is both x and y have the same distribution, and their PDF is given by this formula, is the PDF instantiated at s is equal to the probability that a bus inter-arrival time is larger than s. That's a pound probability. Because it's a pound probability, remember that 0 is equal to t0. So I could have written this as the probability that an arbitrary bus inter-arrival time is larger than s, which is also given by this integral from s to plus infinity of the PDF of the bus inter-arrival time. So that's the generic formula here. If we take the average of that, so if we integrate this PDF, so the integral of s fx of s, that will give me the expectation of the waiting time. We'll see that the expectation of the waiting time is the same as the expectation of the time elapsed, and will be given by integrating this. We find lambda2 expectation of t1 squared. This is exactly the formula we saw a minute ago for Joe at the bus stop here. There is a little caveat here. If time is continuous or discrete, there are small distinctions. Integrals replaced by discrete summations, and there are small distinctions, but most of the time we will ignore those distinctions here. And the expectation of z of t is lambda expectation of t1 squared. The expectation of z derives from the PDF of z, and the PDF of z is the PDF of the t, the time between intervals, multiplied by s. So the probability that we find an interval of duration s is a product of two things: the probability that an arbitrary interval lasts s multiplied by s here. If we multiply by s, we need a normalizing constant, and it turns out that the normalizing constant is exactly the intensity of the point process. So those three formulas, x, y, z, they are obtained by a straightforward application of the inversion formula that we saw. In fact, we did it here for the waiting time, for the computing the average. If we do it for computing the PDF, we could do it for instance, if we want the PDF, instead of computing the average, we compute the expectation of an arbitrary function of xt. That will give us the PDF, as we discussed several times here. This formula is leading to what is called a paradox, an apparent paradox that comes from the confusion of viewpoints, which is called Ferris Paradox. Ferris is the author of a very famous probability textbook. So people of my generation learned probability in Ferris probability books 1 and 2. And he brought to light exactly this paradox. So if we assume that there are lambda buses per hour, then the expectation of the time between bus intervals is 1 over lambda. But when you and I arrive at the bus stop, we will see, as we said, 1 over lambda plus lambda, the variance of this. That's what we discussed a minute ago. But sorry, if we estimate, a minute ago, we had the waiting time, so there was 1/2. But if we're interested in the interval that is sampled by somebody who comes to the bus stop and that did the experiment I mentioned ago, will always be larger. It will be the value found by the system operators plus lambda v here. So the estimate that we do, if we come into the system, we sample an arbitrary interval and we look at its length, which appears to be a standard way of sampling things. Well, it will not provide the same thing as the estimation we do if we know the simulator, we know how the intervals are generated, and we say, well, I know the distribution of the interval of the duration. If I know the average time, for example, 1 over lambda, in one case, I will find plus lambda v here. So this apparent thing is called Ferris Paradox. The estimate that we find is always larger. And as many paradoxes, once we know where it comes from, we can explain why. Well, we know it comes from a sampling. When Joe samples the intervals, Joe samples the intervals in which Joe arrives, and Joe is more likely to arrive in a large interval. In contrast, when the system does its averaging calculation, it takes all the intervals with equal probability, takes them one after the other, looks at their duration, and divides by the number of intervals. So all intervals play the same role in the second case. In the first case, when Joe arrives, you're more likely to find large intervals. So this is exactly putting the finger on what is called the sampling bias. If you do big data analysis somewhere, if you do queuing theory, if you do simulation analysis, it's very possible that biases like this occur. How? So the question that should come to mind is, once you decide to estimate something by sampling, I mean, how did you sample? Does the sampling introduce some bias? That's the key theme of this chapter. By the way, if you remember, yesterday we discussed in a apparently radically different setting, which was sampling the sizes of flows measured on an internet router. And we saw exactly this formula. We saw that the size of flows sampled by an arbitrary packet, where you ask the packet, what is the size of your flow, versus the size of a flow sampled by looking at the flow list and consulting all the different lengths that we have, then they're related by the similar relation. One PDF is equal to S times the other PDF multiplied by a normalizing constant. Well, this is exactly the same thing. If we think of flows, if we reverse the order of packets such that, or we rearrange the packets such that all the packets of the same flow are put together, then we're exactly in the same setting as together, where end of flows corresponds to events. So this is something that we had found by the heuristic of yesterday. So this paradox provides interesting paradoxes. For example, if we have a Poisson process. The Poisson process is the simplest of all processes, but sometimes not so easy to reason about. So let me recall what a Poisson process means. The Poisson process is a process that could be used to generate those arrivals of instance here. And one way, there are multiple ways to think of it. The major property is it's memoryless. But one way to think of it, to truly make sense of what is memoryless, assume that you have discrete time. not continuous time. Of course, Poisson process is for continuous time. That's why it's difficult to really reason rigorously. But my imagination of it is, assume you are in continuous time, but somewhere, if you look at the nanosecond or the picosecond time scale, you can reason in discrete time. So every picosecond, you flip a coin, and with a probability equal to lambda times 1 picosecond, which of course will be a minuscule probability, but the probability that's non-zero, and that's proportional to lambda. So with this minuscule probability, at every picosecond, you flip a coin, and if the coin returns 1, you say there is an arrival. That's one way to think of the Poisson process. And the coin flips are independent. Whenever you flip a coin, you flip the same coin, ignoring what has happened before. Of course, it's a biased coin. The most likely outcome is the coin will say no, but with small probability, the coin will say yes. So that's one way to think of the Poisson process. And if we think about it in this way, then it's easy to understand that the time, if you ask the question, I arrive at an arbitrary point in time t, and I ask, when will the next arrival occur? Well, when will the next arrival occur? Well, the time it takes for one flip of the coin to return yes. And if you ask the same question, what is the distribution of the time between arrivals? So that's a pound question. I put myself at the beginning of an interval and I ask, how much time will it take until the next arrival? Well, the answer is the same. The time it takes for at least one coin to return yes here. So we see that the distribution of the waiting time is equal to the distribution of the time it takes between two intervals, which is a bit paradoxical, but comes from the memoryless property, which of course we should find out by application of the previous result. We do find that the residual time as a distribution, which is given by this formula, which is the exponential, same as the distribution of the time between intervals when we observe it at event times here. Interestingly, in the reverse direction, we find the same thing. This is quite general. We find that in the theorem here. The time elapsed has the same distribution as the time in the future. So in some sense, we have, if we look only at the arrival of instance, time is reversible. We can reverse time and things from a statistical viewpoint play the same role. So the past time is exactly the same. Now, if we think of my coin flipping analogy, it's easy to understand why. I am at time t and I ask the question, when is it that the last arrival occurred? Well, to have the answer, or to simulate a possible outcome of the answer, I need to ask each of the picoseconds in the past, when was the answer of your coin yes here? So since the coins are flipped independently, then I can, the answer is as much time as it takes for at least one coin flip to return yes, which is the same answer as in the future. Therefore, they have the same distribution. Now, if we ask the question, what is the length of the interval in which you are, then it's easy to see that it is the sum of xt plus yt. And with this coin flipping analogy, y and x are independent. So the time elapsed is independent of the time to go because of this coin flipping, that at every picosecond we do things independently of everything else. So the time z is the sum of two random variables. Each of them is exponential. So that has a name. It's called the Ln2. In general, the sum of k exponentials with the same rate is called Ln(k). So this is an Ln2, and of course Ln(k), when k gets large, will become a Gaussian distribution, but where 2 is not large, so this is something that is less heavy-tailed or has a less large tail than exponential. It's closer to Gaussian random variable, but is not exactly a Gaussian random variable. It's called the Ln2 distribution. In particular, its expectation is 2 over lambda. So in average, even for the Poisson process, if you sample an average interval here, you'll find a duration 2 over lambda, which is twice what you would expect for the Poisson process, even with the memoryless property. Well, this is how we explain all those apparent paradoxes. Okay, time for a little quiz. In a slightly different setting now, I have sensors that sense events. The time between sensing is very periodic, but not exactly. So it's Gaussian with some mean mu and some variance sigma square here. Why is that? Well, we find that very often, even things that are periodic, if they're strictly periodic and synchronized with GPS, of course, sigma square will be negligible, will be 0. But if the sensing interval is due to, for example, refilling something, then it fills at a constant rate, but in physical systems, there's always some noise. So the exact time will have some variability. So that's a model that we frequently find in the Internet of Things when we use sensors, for example. Now assume an engineer comes and check the current sensing interval. So you come into the machine and, for example, assume the machine prints a display that says the last sensing interval was at this time with the local clock of the machine. And you wait for the next to come. So you come inside an interval and you measure it. In average, what will the inspector or the engineer find? I close the poll in a few seconds. Closing. And the correct answer is the third answer. Well, first, that's a very easy question because that's a closed question where you have to choose from one of those. I mean, as a performance, when we do a performance evaluation study, we take the hat of a physicist. We observe a system and we try to do things as good as physicists say that they do. Not as good as they do, but as good as they say that they should do, which means you should be aware of things like, is it physically plausible? Here, if I say the sensing interval is Gaussian with mean mu and variance sigma square, the reflex you should have is what are the units? Mu and sigma square are what? So my sensing interval is a time, I assume. It could be also measured in distance, what in kilometers or whatever. But here, let's assume it's a time. So mu will be a time. Mu is the average of my things. So it's a time. If I measure a time, the average of what I obtain is a time. Sigma, with the standard deviation, is also in the same unit. Right? So sigma square is a square. The variance is a square of time, but sigma, which is the square root of sigma square, is a time to the power 2. So if I look at this formula here, this one appears to be correct. It's a time. This one is certainly invalid. So B cannot be because it's a time. If time is measured in second, this is second plus second square. This one would be second plus second. So A and C are possible candidate. 1 over mu does not make sense. It is in second minus 1. Here it is in second minus 1 plus something unit less. So it's also suspicious, it cannot be. And here, same thing, it is in second minus 1 plus second. So only C and A are potential candidates here. Now, if we do the calculation, if we apply the formula that we saw before, well, the formula says the average time here, the average interval that is sampled by an expector that comes in the middle of an interval, is the average length of an interval as seen by the simulator that sees all the different interval lengths, plus lambda v. Well, lambda is 1 over the mean interval. So lambda here is 1 over mu. So that's mu plus 1 over mu times v, and v is sigma squared. So exactly this formula is answer C, which is the only possibly correct answer here. Oops. Okay, so that's the solution. Last question and last quiz of the day. Same question now, but instead of Gaussian, so interval that is very deterministic, in particular if sigma is small. Well, by the way, in the previous thing here, you will see if, say, mu is 10 seconds, so the sensor wakes up every 10 seconds, but with a standard deviation of 2 seconds, so sigma squared is equal to 4, then you will find that the average interval that we find here will be 10 plus sigma squared 4 divided by 10, 0.4. So this term is very small for a Gaussian distribution, right? It will be 10.4 here. Sigma has to be small if mu is a positive quantity that is Gaussian, right? Which corresponds to what we saw. The tail of a Gaussian distribution is decaying fast. Now, I assume things are more random. We don't have Gaussian noise, but exponential or Laplace noise or something similar. The interval between events is exponential. So this is one way of modeling something that's completely random. We don't know exactly when things happen. This is what is used, for example, for modeling arrival of calls into a system, into a calling center at the peak hour. Of course, if you're at the peak hour or at the off-peak hour, you know the intensity will be different, but if you do a microscopic study of, say, 15 minutes during the peak hour of a call center, this is the model that has been validated by many studies. So the sensing interval, or here the interval between two calls, is exponential with rate lambda. If we do the same question as before, what will we find in average? So the inspector of the call center monitors the intervals. What will she find? I close the poll in a few seconds. Closing. And the answer is 2 over lambda. There are multiple ways to see that. I mean, first you can remember that I just explained it a few minutes ago when explaining that z of t is the sum of x and y, and they're independent, and each has an average 1 over lambda. Whether they're independent here doesn't matter. So the expectation of z is 2 over lambda here. Right? So we could also apply the formula that we had before with the variance, and we know that the variance of the exponential distribution, we know or we don't know. If we don't know, we quickly look up Wikipedia and we find it's 1 over lambda squared. So either way, we find 2 over lambda here, which is, as we said, Ferrous Paradox is the textbook example that explains exactly what I mean when I say the importance of the viewpoint or the importance of a sampling bias. Voila, that's all for today. Thank you very much for your participation. Enjoy the quiz that you will be able to complete next week when we have completed the second part of this quote on PAM calculus. In the meantime, take care.